silly, but oh well. I'm going to copy this into the other live stream chat to be like, sorry, don't know what's happened. I think I'm now live. Yes, I am. Hi all. Sorry about technical difficulties. Apparently when I set up the live stream previously, I'd set it up to be a streaming software as if I was like a gamer. And I don't know how I did that, basically. And so it was that like, you need to give me a streaming software to tell me where, you know, the gaming is happening. And I was like, no, just let me go live with the camera, please. I'm not using my mic either now because of the panickedness of it. I'm going to post this link to the other live chat so other people can actually see that. I'm going to pin that to pin message so people actually find it. Oh God, where's, oh, it's there. I've lost the tab now. This is going so well. Anyway, welcome everybody. So today is going to be me signing a load of books for you all, basically. So this is the US copy of my book, which some of you will have now seen. It's got lots of awesome extra little visuals in it as well that the artist has done. So it's really, really pretty. Because it's pandemic, my publishers can't really get a load of books to me. That's not environmentally responsible, and I can't really get to the States. So I'm going to be signing these little book plates, and then essentially I'll send those back to the US and publishers will stick them in there, and then you'll be able to buy a signed copy. So I have 250 of these. That's how many of the signed copies there's going to be. At 8:45 tonight across all my social media channels, the link will go up to where you can buy one of those books so that, you know, if you want to, you can buy one. But there's only 250, so there's a limited number. So I'm going to start signing. I have got, and Sam is my helper over in the corner who's manning the chat as well. So he's going to tell me like what people are asking in the chat and sort of throw some questions at me. But I also ask people on social media to throw me some questions beforehand as well. So I'm going to grab a couple of those first just to get us going. I'm going to try and sign it where you can see me actually signing it. So you can be like, oh, maybe that was mine. So yeah, I'm just going to kick it off. Let's go, 250 to go. All right, here's the first one. There we go. First one done. Woo! All right, there's the done pile, much smaller than the not done pile. All right, what's the first question?
So the first question is from Slit Squared on Instagram, who asks, when a star goes supernova, are heavier elements split so that there is hydrogen released to support forming new stars?
Yes. So it's a sort of common misconception is that when a star dies, it has used up its entire stock of hydrogen. And then when it goes supernova, you know, there's no hydrogen sort of expelled back out. It's literally just helium and heavier elements that's put out into space, basically. But actually, it's only like the sort of inner 10%-ish of a star in the actual core when nuclear fusion takes place. And so actually about 90% of what's thrown back out into the surrounding space is hydrogen. And yes, new stars will form from that hydrogen, but just also with some extra heavier metals, as astronomers call them, mixed in, like oxygen, nitrogen, that kind of stuff. Metal being anything basically heavier than hydrogen. Oh, my Y went funny on that one. If you get that one, my Y went funny. Sorry. Yeah, good question, but common misconception. Also, ignore my plaster. I had a run-in with a knife chopping some coriander. It's fine. It's just one of my nails is ruined and I'm still mourning it. It's okay. Next question.
Next question from Giovanni. What is the approximate temperature of space?
Oh, so we kind of know this from the approximate temperature of the cosmic microwave background, which is that echo of the Big Bang. What we're really measuring is sort of the energy in each different part of space. But I know the number off the top of my head is about 2.7 Kelvin. So 2.7 degrees above absolute zero. Molecules have absolutely zero amount of energy to play with. So yeah, 2.7 degrees Kelvin. Good number to know. I guess it's like 42, but 2.7, pretty chilly. Oh, if you're wondering where we are, we're back up north because the UK government is now allowing people to stay over at other people's houses. So we've come to see family. So this is sort of family dining room that we're in at the minute. Just explaining what we're up to. You're all curious. I've messed up my Y on that one again. Sorry. I thought about numbering these, but I thought it would take me too long. All right, next question.
So next question from Karthik.
Karthik, can you all, I don't know if they can all hear you. Let me know in the chat if you can't hear Sam, by the way, and I need to repeat questions.
So the question is, how do we find the mass of galaxies, including dark matter?
Okay, how do we find the mass of galaxies? So there's a couple of ways we do this. So the first one is using something called the mass to light ratio, which is essentially we, have a measure of how bright a galaxy is, and how bright a galaxy is essentially based on how many stars it has in it. So if you sort of know how bright it is, and you generally know what distribution of the types of stars you have in that galaxy, you can then get a rough mass of the galaxy using whatever you think the mass to light ratio is. And that's based on models of, what kind of different types of light, different types of stars of different masses give out, etc. The dark matter component comes usually from gravitational lensing, which is where the galaxy acts as like a lens, so that background light is bent into arcs, sort of like a wine glass stem does. I'm supposed to have a glass of wine during this as well. Oh, technical difficulties still. So where was I? Wine distracted me. So gravitational lensing tells you how much matter is there that is actually lensing it. And that's how we know there's dark matter, because it tends to be 10 times as much visible matter that we actually see when we do the mass to light ratio. But also you've got galaxy rotation curves as well, give you an approximate mass too. So there's lots of different ways to do it. But generally, we look at the brightness. And that's one of the things you have to sort of work out as an observational astrophysicist, is that the number you can measure is brightness, whereas the number that simulations people and modelers are using is mass, because that's what they can measure in their simulations from like number of particles. So we either have to convert into mass, or they have to like imagine, well, if these particles have this mass and this is this star, then that's what brightness they're going to end up with. So either way, you have some sort of step in the modeling or the observation that makes it difficult to compare them, and it's always something you have to take into account if there are any biases in there. That one looked like it was done by a child, but I'm rolling with it. It was a bit Comic Sans MS. Anyway, next question.
Okay, next question from Connor.
Hi, Connor.
What's the most interesting piece of research you've read recently?
Oh, there was this really cool talk I went to the other day that was from a simulations person. And I think as someone who works with data from telescopes, I'm always like, ooh, tell me more about your cool simulations, because I don't think about it enough. And they were simulating what happens in terms of, where star formation in galaxies stop first. Is it in the middle and then it works outwards, or is it outwards and works in? And the data that we've got at the minute is showing that a lot of it is inside out. So the stars stop forming first in the center, and then it moves outwards and outwards. But in the simulations, they're finding the opposite, that there's a lot of hot gas in sort of what's called the intergalactic medium, or the gas that's between galaxies. And that's actually somehow cutting off star formation on the outskirts of galaxies first and working their way in. And it's really interesting to think like, okay, well, what's going on? Is there some bias in the data? Is there some bias in the simulations? Like, what haven't we thought of? And I'm just really intrigued just to see how that comes out, because that's going to be sort of what I'm working on as well. I'm going to try and find observational data of when the star formation is stopping and where in galaxies. And so I'm going to be able to directly compare. And that just got me like really excited the other day when that talk, spiced up a day in lockdown, which was nice. So next question.
All right, so we're going to dip into the live chat now.
Ooh, live chat.
Question from Marcus.
Hi, Marcus.
What was the most interesting part of your trip to CERN?
Oh,
other than meeting the guy in the picture.
Roger was awesome.
And were there any key things you took away for your future work or studies?
Oh, okay. I think the most interesting part, it was sort of twofold. It was seeing how everything works together, if that makes sense. Like, it's this huge complex, right? It's a little mini city in itself, and it's sort of incredible to think how it all works together and how like everyone comes together to make stuff work as well. I mean, obviously going down underground and seeing the detectors was just amazing and overwhelming and incredible. One of the most interesting things I learned was that there is obviously fire safety in the detector tunnels and in the detector itself. Like we saw CMS, and they have this huge big like foam fail safe where like the whole room will just get sprayed with foam. And of course they had to test that as well, which I think is fantastic. Things I'll take away for future studies is I had a really good chat, which I haven't edited yet, sorry, with April Cridland about the experiments that they're doing with antimatter. And she was talking about the idea of like whether antimatter has anti-gravity, like does it fall upwards? And I this idea fascinates me, and it could, you know, play into sort of astrophysics as well. So hoping that maybe like if we understand that better in the future, there'll be somewhere where we can like maybe do some sort of observational test of it, maybe in like 10-20 years time. And that would be really cool to do like with a PhD student in the future when I hopefully have a permanent job. Fingers crossed. Next question.
All right, let's go to Twitter. So we've got a question from Martin. Do black holes distribute relatively evenly throughout a galaxy or the universe, or do they form in clumps?
Oh, okay. They're generally distributed in the same way that stars are distributed in a galaxy, right? Where you have sort of like the central, you know, CBD of a galaxy where it's incredibly, CBD is in like central business district, it's in like a city. That's not like an astrophysics term. Like it's a very dense area, whereas you've got like the suburbs on the outskirts where like where we are, where it's not as dense. And so you generally will find more black holes just where there's more stars, because obviously you've formed the stars when you form the black holes when the stars have gone supernova. I guess you'd always find more black holes wherever you've got a larger fraction of heavier stars forming. But typically, like we have something called the IMF, the initial mass function, which is essentially like how many stars of each shape do you make? Sorry, not shape, mass do you make? And there's sort of like a curve that you can draw, you know, and generally that we think that is universal. There's a big sort of debate out about whether that does vary from galaxy to galaxy, depending on like metallicity. And there's people who spent their entire lives like studying the IMF and whether it is actually changing either with redshift or with environment or metallicity, like I said. And so if that would change, then and you had more heavy stars forming, then you would form more black holes, obviously. But generally, they just tend to be distributed the same way that stars are. So might not be the same though in the early universe. Who knows? Where are we going next?
So live chat. So there's been a few questions from PhD students, actually.
Oh, hey, PhD students. You can do it. You can do it.
This one's from Sarah. And Sarah says, I wonder if you have any advice about staying sane and also productive during lockdown as a PhD student.
Sane and productive. Productive. To-do list, see friend. Honestly, I've talked before about how I bullet journal and just a daily to-do list just to try and keep on top of things, but also to help you track like if you're getting stuff done. Recognizing when you're actually productive. I am much more productive, so like 3-4 o'clock, so mid-afternoon than I am in the morning. So I'll put different tasks to do at different times of the day. I know I need to concentrate more on something, and just find out what it's for you. You don't have to stick to a 9 to 5 in lockdown. You know, if you find that you're most productive like after dinner or something, like do it then, or you know, like whenever, and try and do that kind of stuff. As if for staying sane, just friends and family. Like as soon as you find that you're getting stuck in research or stuck in a rut, whatever it might be, just call someone, have a chat, you know, call your colleagues, bounce an idea off them, tell them that you're really struggling and this is why. And you never know, they might, you know, be able to come back to you. I think just having a chat with anyone just reminds you that you're human and you're not just all about the data or whatever it is you're trying to do, the code. But I can imagine doing a PhD in lockdown is very difficult. My PhD student at the minute, you know, we've been talking a lot and saying it's okay not to be productive right now, for whatever reason. There's a lot of stuff on everybody's minds, and so that's okay, just as long as you at least acknowledge that and also like log it so that your supervisor and funders and all sorts of that, you know why it was an issue. So, you know, maybe relax your standards of what makes a productive day as well, and that also just sort of help your mental health a little bit too. But comedy shows too, can definitely recommend some comedy shows if that would help. We watched Sex Education recently and it was so funny. It was great. And The Good Place. Everyone should watch The Good Place. And the new Eurovision film. And someone commented before saying, well, I sing Ya Ya Ding Dong. And I do love that song. I'm not going to sing it. Or will I? Next question.
Another question from live chat.
Yeah.
Is it necessary that galaxies have to have a black hole in their center?
Necessary? Oh, that's like a different question, right? Like, so like, what about, is it necessary for them like literally to exist? Like, would they not be a galaxy if they didn't? I think that's a really interesting question, because I think it comes back to the like what formed first question as well. Like, galaxy formed first and the black hole seemed to the center, or did the black hole form first and the galaxy form around it? I don't think necessarily a galaxy wouldn't, like as in like a collection of stars, wouldn't be bound if there wasn't a black hole in the center. It's interesting to think when you look at dwarf galaxies, especially, that are very like diffuse, like they don't have that sort of central clump of stars, and they're very faint, and they're sort of maybe like tens of thousands to hundreds of thousands of times the mass of the sun, rather than like, you know, billions, tens of billions times the mass of the sun, like so the Milky Way is. So they don't have necessarily what we call a supermassive black hole. There may be sort of more of these intermediate mass black holes that people are looking for. So in essence, they're still galaxies and still have a black hole in the center. But I think, you know, there's enough mass in the stars to bind the galaxy together. So I don't think it's necessary as such, but I think it definitely comes back to like how you define a galaxy. Interestingly, there is no agreed upon definition for what a galaxy actually is, which I find really interesting. And just a little bit of a fun fact tidbit for all the 60 Symbols fans out there. I had to make a 2-minute video about any topic in physics or science for my 60 Symbols application, like for the job, you know, the research job that was going at Nottingham, where it's just you also happen to make videos. And that was what I made my video on, was the fact that there is no actual agreed upon definition for a galaxy. And I remember it was really cringeworthy when I watch it back, but it was pretty good. I tried to do the like walking and talking thing to be like, I'm impressive, I can walk and talk at the same time. I'm sighing and talking at the same time right now. So that was the done pile, by the way, just so you can compare the done and not done. This is done. This is not done. My hand's still not big enough to pick them up, but I think we're about a fifth of the way through. So fun. I hope people managed to find this coming from the other live chat. That was so hilarious, but oh well, here we are. I'm an astrophysicist, but I can't work YouTube live. Not a rocket scientist, am I? An astrophysicist is the difference. Right, next question.
So we're going to go with one from Jujubean.
Jujubean, great name. Jujubean, so cute.
The question is, how do dwarf galaxies differ from regular galaxies, and what can we learn from them?
Yeah, because there's no agreed on definition of what a galaxy is, right? It's hard to say, you know, how they definitely differ. There's no hard threshold that you cross, all of a sudden that's classed as a dwarf galaxy, and that's not, you know. There's sort of like, people tend to do it by mass in terms, or brightness, of how bright something is, but I mean generally they just tend to be very diffuse. Anyone who's seen the small or large Magellanic Clouds in the southern hemisphere, right, they're just sort of wispy, diffuse things in the sky, and so they differ in the fact that there are much less stars in there. It's very interesting to study dwarf galaxies, because you kind of think, well, did all galaxies start off that way, and did they merge together on these sort of big merger trees, we call them, to make what we have today? So they are a very interesting area of astrophysics. I have a colleague in Portsmouth, Sam Penny. Hi, Sam. She works on dwarf galaxies, and she does the black holes in the center of them as well. And it's really, really interesting, I always think, because it's sort of on much a smaller scale. They're almost like, and the other thing is, you know, where do you cross the boundary between, like, you know, globular cluster of stars into dwarf galaxy as well? It's really interesting. It's like that sort of boundary between like planet, brown dwarf, etc., like big Jupiters, brown dwarfs, all that kind of stuff. I made that video on Planemos a while back, if people remember. It's a similar sort of thing. So we can learn a lot from them. But I like to be able to see my galaxies, and dwarf galaxies tend to just be little smudges. So give me a grand design spiral any day. That one I went very like floofy with the Y. I'm embellishing things now. I thought about writing my last name, but I figured it would just take a lot longer. And you all know me as Dr. Becky anyway. So my last name is pronounced Smethurst, in case anyone was wondering. Gotta put on that Lancashire accent to say it, Smethurst. Next question.
Okay, Mr. Castle.
Mr. Castle.
On live chat. Is there a lower limit for the size of a black hole?
Yes. One that are formed in supernova, definitely, because you know there's a threshold between when the star collapses down. Do you get a neutron star or do you get a black hole? And there's that limit of sort of going from a neutron star to a black hole that we don't quite know where that is. That's going to be in this week's Night Sky News, the most massive neutron star, the smallest black hole. This month's even. But like you can get things like primordial black holes that were supposed to form in the very early universe, that, you know, the tiniest little clumps of matter as they were sort of fluctuating in the early universe will have had an area that was so dense that a black hole would have formed. So I'm going to say no, probably not. But I'd have to probably go chat to the theory friends down the hall just to check. But I don't think so. Next question.
So this one's from Amy. Quite an interesting one here. So how did you choose one particular topic for your PhD thesis?
Okay.
She says because space is so interesting.
Yeah. So the funny thing was I did my master's project at undergraduate in Durham, and the way they pick your master's project is you got this big booklet, and Sam will remember this as well because he did the same thing, and like you read all of the projects that are available from the supervisors and you list your top 3 projects that sound really interesting. And the top of my list was all of the moon projects, because it was like working with images of the moon, like measuring craters, all that kind of stuff. And I was like, that sounds amazing. I've always loved the moon. And then I didn't get any of those. And I got given instead a galaxies project. And I was really disappointed at the time. I was like, oh, it's actually boring. And then I actually loved it because I was working with images of galaxies. I was like, wow, this is so pretty. And like had a great time. And really enjoyed it because it was much sort of like bigger picture stuff, but it wasn't like too big. It wasn't like cosmology, which is like the whole universe and the Big Bang, and you just get a little bit lost in, you know, like reducing the data down to something that's, you know, understandable. This felt like sort of, here's my subject that I'm studying, this galaxy, and I can reduce this one galaxy down to this property, and etc. And I found that really interesting. But then when I was applying for PhDs, I was like, oh, I want to do something different. And I was still sort of like enamored with the idea of working with planet data. And I thought I wanted to do like exoplanet stuff because that was really, you know, like the big buzzword stuff at the time. Everyone wanted to hunt for exoplanets and model what they were doing. But then when I went to the PhD interviews to actually talk to the supervisors, and this is incredibly important because when you go to the interviews, you have to make sure you get on with the person that you want to work with, and also that you find their project interesting. And so when I went to talk to people and I was like, okay, so what kind of data will be working with exoplanet stuff? And they're like, oh, it'll just be like a light curve. It's like a planet passes in front of a star. And I was like, oh, it's a bit boring. And I was like, oh, do you get to go to telescopes and do this? And they were like, no, it's all done by space telescopes like Kepler and TESS. And I was like, oh, I kind of want to go use some telescopes. And at the same time, I was then talking to the galaxies people because they'd seen that I'd done my master's thesis on galaxies. And they were like, oh, so you want to come work with us kind of thing. And I talked to them and I was like, actually, this sounds well fun because look at all these cool images they have. And look at, they've been to telescopes. And actually, yeah, I am really interested in that question. And that kind of would follow on from my master's thesis. And also I met at Oxford in the end where I ended up choosing to go, I met the Galaxy Zoo people. And I loved the idea of a project that was possible because of the efforts of the public. And they were really keen on like science communication as well, and like giving back to the volunteers who'd classified the images of galaxies and explaining, you know, the work we were doing back to them. And I thought that sounds really fun. That sounds great. This is something I'd really want to do. And so that's how I ended up ending galaxies. And sort of I like, because it's independent research that your PhD is supposed to be. Obviously, you get guided by your supervisor in the first year or so, but then the idea is that you come up with your own questions, like off the back of the stuff I did in my first year. And I was like, actually, I find like supermassive black holes the most interesting. So I want to really study how they interact with their galaxies. And then I sort of molded the PhD a little bit that way into the galaxy supermassive black hole, like interaction kind of area. And that's what I do now as well. And so that just came from, just experience. And I think when I was in my PhD and going to all the lectures that you had to go to at the beginning as well, being like, okay, this is what's going on sort of like right now in this field in astronomy. I was like, yeah, I picked the right field. So yeah, that was good. Was there like an end point of that question? And it was like a second like follow-up, or did I answer it all?
Quite possibly, but I'll scroll down.
Oh, never mind. Sorry, Amy.
I'll try and find it again. Right, next question from Russell on a live chat.
Hi, Russell.
Is it possible for a small black hole to take in so much material that it gets blocked like a drain? That's the best way you could describe it.
No, I get it. That's a really cool question. So yes, actually, there is something called the Eddington limit, which is when the material that's spiraling into the black hole, because it's traveling so fast as it spirals in and is accreted, the pressure massively increases around there because it starts to also radiate. So you get radiation pressure. You know, people talk about light sails, like using light from the sun and the particles hitting into a sail, and that gives them energy to, use them as perhaps a spacecraft. Same kind of principle here. You have the material is heated up, it goes radiation pressure, and that actually stops more material coming in. So when you have a mass of a certain black hole, you know the Eddington limit tells you that, say, it can only accrete 3 solar masses a year, and that's its limit because it's reached its Eddington limit at that point. So in essence, yes, the Eddington limit is like a bottleneck a little bit. Good question. Oh, my light is dying. It's now but like randomly pulsing as if it's sending me an SOS message. Turn that off. Oh, the video is so grainy as well because I'm on my laptop because my phone never worked in the end. I'm really sorry about the video quality, everyone. Oh, also, at the end of this, I thought I'd read my preface as well when I finish signing. So you'll get to hear me read an excerpt from my book, which will be fun. So stick around for the end. Oh, and to all the Canadians who are asking, were they able to buy a signed book? I went to the link and I don't think you can, unfortunately. You're classed as international shipping. Like, you're not going over an ocean. So I'm really sorry about that. And I will speak to my publishers about doing something for you guys as well, because it's not fair to leave you out since this is the US and Canada version. But US people will definitely be able to buy one. And happy Independence Day to all of you in the US for yesterday. I hope you've had nice weekends, safe, socially distanced weekends. Next question.
Okay, so quite a few people have asked questions on this topic.
Okay.
But could you talk about the latest ideas that have been spoken about in terms of the dimming that we observed on Betelgeuse?
Well, I could. I'm just going to go in this month's Night Sky News, though, and I kind of don't want to spoil it. But Betelgeuse is doing strange things again. If you remember, Night Sky News is from sort of January time. It dimmed massively, and people thought it was a supernova, but it's much more likely that it was possibly dust at the time, was the hypothesis. Now people are saying that it's probably something like sunspots, like sunspots we see on our own sun. You get star spots as well. But people are saying to explain the dimming, they would have had to be huge, like, covering half the star spot kind of thing, which would be unheard of, but not necessarily something that couldn't happen because, we don't know everything about the universe. We don't know what's possible and what's not necessarily. So, yeah, I'm going to talk about that more in Night Sky News, but star spots could be very exciting. I always love Night Sky News. It's a fun thing to do every month, just be like, wow, let's have a recap. What's been going on? I think I'm about I'm half done now. I'm at least more than half done, maybe. The done pile is looking a lot bigger than the not done pile. Ugh. Just about. We're getting there. I've not got hand cramp yet either, which is great. You're being kept entertained by the live chat.
Yeah, good. I'm just going through.
Trying to keep up. I can actually see it on my screen. It's constantly flicking up. So many people asking questions. It's awesome. Trying to be the friendly neighborhood astrophysicist that I know that you all want in your life.
All right, we've got a question here from Perry.
Perry, the platypus. No, like
no,
10% of people will get that
Perry.
joke. Perry.
The question is, do planetary systems form near the center of galaxies? And if so, are they stable? I ask because there must be a lot of gravitational pushing and shoving.
Yeah, so I think I remember reading a study on this about the incidence of planets dependent on the position in a galaxy, because yes, it is much more chaotic towards the center you get, and so you're much more likely towards the center of a galaxy to have planets flung out of the system, and that's not unheard of. When we sort of simulate planets forming, there are a lot of things that are thrown out, and so people had expected for a long time to have, visitors to, say, for example, our own solar system that are from different systems that have been thrown out. And that finally happened with Oumuamua about 3 years ago. There was that weird sort of cigar-shaped, is it a comet, is it an asteroid thing that sort of visited from a different system. And so you are much more likely to have these sort of rogue planets that are thrown out and are not attached to any star anymore, the further in towards the center of a galaxy you get. Obviously, the material is much more denser there, so the probability of forming a planet is probably greater because you've just got so much more material. So it's an interesting one. It's kind of like a little, it's like two sides of a coin, I guess. It's like a balancing act of like forming more, but more getting thrown out, I guess. I need to look up that paper again just to check what it was. I'm pretty sure there was like a sweet spot somewhere. But I need to check because I can't remember who wrote it off the top of my head. It's a long time ago. Sorry. But that would be a fun video topic, actually. Maybe I'll add that to my ever-growing list of video topics I should make. And see what we can find out about it. It sort of coincides with like the galactic habitable zone, right? The Goldilocks zone in the galaxy where that's to do with life rather than planet formation as such. But yeah, where you can have life on a planet because there's not too much radiation from the supermassive black hole in the center, and there's also not radiation from intergalactic space as well. You know, that sort of sweet spot where we are, sort of in the middle of the suburbs. Oh no, my pile is falling down. Okay, next question. Hit me.
Okay, another question from the live feed. Why is it that the center of galaxies are so bright, even if there's a black hole at the center?
Yeah, so another common misconception is that growing supermassive black holes are actually the brightest objects in the universe. Sounds a bit weird when you first say it, but it's that material that's spiraling around it that we were talking about before in terms of the Eddington luminosity as well and the Eddington limit. The material is essentially just sort of superheated, and you get a lot of radiation coming off it that hits the surrounding material as well and can cause electrons to be excited and will jump up any energy levels, drop back down, give out emission. Also, you get stuff like Bremsstrahlung radiation as well, like X-ray emission from electrons moving through various different fields around the center of the galaxy too. So you get everything from very bright hydrogen emission to X-ray emission to radio emission to gamma rays as well. And so they're incredibly, incredibly bright, also in the infrared, optical, UV, all across the wave bands. And it's actually really funny because like if you speak to someone who is a galaxies specialist who's interested in galaxies and the sort of the AGN, what we call active galactic nuclei, these growing supermassive black holes, who get in the way of them studying what's going on in the center, they'll call them like a contaminant to their data. Whereas if you talk to someone who's interested in the actual growing black hole itself, then the galaxy is foreground that gets in the way. And I was at a conference once where it was sort of the meeting of those two groups of people, and it was really funny to hear them call my precious galaxies just like foreground all the time. And I was like, it's the interesting bit. So yeah, that's why they're the brightest things in the universe. It's why like quasars, right? We see them at such huge, huge distances because they're so bright, especially in the X-ray. This is why black holes are so cool and my favorite topic because they're just awesome. So contradictory. Black hole, nothing that light can escape except from the disk around it where there's material spiraling that hasn't crossed the event horizon yet.
Okay, so another question from Raynan this time.
Raynan. Hi, Raynan.
Is it possible for an elliptical galaxy, given enough time and interaction between the stars, to turn back into a flat disk as the stars slowly find a preferential way of motion?
No, it is not. At least people don't think it is anyway. So once you have a truly elliptical galaxy, so a true geometrically elliptical, so sort of like a kiwi in shape is sort of the best thing. It's called triaxial. So if you can chop through a kiwi 3 different ways, and you'll always get a different cross section, unlike like an orange where you can 2 cross sections the same. Anyway, and to be that physical shape, the stars have to be on completely chaotic orbits, and you've massively increased the angular momentum. So you would have to somehow remove angular momentum from the system to do that. And we do see in simulations when you have mergers of 2 galaxies, that these are the mergers of what's thought to create this chaotic environment where the stars aren't on, a nice ordered rotation around the center of the galaxy anymore in a disk.